Monday, April 26th. One morning, I heard an unusual flapping nearby, and when Don went to investigate, he found this long piece of yellow mesh stuck to the tree outside of Ruth Ogawa's apartment. Skytrack comes rumbling along with a new delivery. Turned out to be prefabricated shower enclosures. I wasn't sure they were going to get it through the space allowed, but after some perseverance and hand signals, the guy down below can't see you. Okay, hand signals. They managed to get it in the opening and set down. Familiar scritching sound drew my attention to these guys spreading stucco at the end of the solarium. Walking up the sidewalk, the south side of the building looked a lot like a tic-tac-toe board. Few days later, when the stucco was covering most of the south side, it looked pretty imposing. Workers in white hazmat suits spread stucco over remaining insulation as they worked toward the assisted living atrium. Checking out the south retaining wall, I saw that they are putting concrete and rebar into the existing wall. Later, I walked past the wall, and this worker was applying a dark chocolate-colored goo that was very stinky. He explained it was waterproofing. Near the assisted living atrium, I saw that they had started pouring curbing and guttering. This crew was pouring concrete out from the lobby entrance of the atrium, but I'm not quite sure what this is going to be. I'll have to check again later. Walking up into Alta Vista, I was greeted by all sorts of beautiful bloomies. Courtyard Garden is very cheerful. Lilac smells so good. I see you've noticed all of these are purple, but I'm not the one that planted them. Fence had been erected around from door 10 toward door 13. Yellow Cat had exposed sewer lines. The worker installed an upright pipe and is now tamping down the ground. Little Cat is trying to keep up with the movement of the dirt, and the truck is just trying to get through. I was happy to see there was a sliding glass door out on one of the IL patios. From the casita wall, I could see them installing framing to eventually pour curbing and guttering around the parking structure of the IL building. On the north side, the scaffolding has come down from the retaining wall and they're smoothing out the dirt, but there's something weird on top. Zooming in, I found broken pieces of brick stuck in the concrete. Oscar said it was to keep the rebar 2.5 inches from the back side of the brick as the concrete dried. I was lamenting to Oscar how long it seemed to have been since P&M was supposed to set the transformer. He laughed and said, "They're setting it as we speak. Go check it out today." We spent a week in Ruidoso recently, so here are a few of the highlights. 10 years ago, fire decimated the hillsides around Ruidoso. I am glad to see new life. Every time we return to this area, I am impressed by the artistry of these huge horsehead gates. To get to our timeshare at the top of the mountain, we had to go through the castle gate. It was actually a business renting storage units. Our patio overlooked the Inn of the Mountain Gods and the beautiful lake behind it. At the entrance to the inn are these 10-foot-tall native dancers. On the lake, there are paddle boats everywhere. What are they pointing at? Above our heads, two brave tourists were using the zip line to cross the lake. At White Sands, we found that we felt very insignificant, like those tiny hikers on the left. Kids were having a blast using saucers to slide down the hills. Storms started rolling in, but it made for a really great picture. Ruidoso is known for its many murals. This one was bright and cultural and a little haunting. Another was iconic and reminded me of my childhood. Driving around town, you had to be careful of what was crossing the street because there were always more coming. Okay, is it safe to go now? From our patio, sunset at about 7:30 was beautiful, but if you waited till closer to 8, there was fire in the sky, and we were mesmerized. Deer walked past our condo daily. We would see herds of elk as we descended the mountain, but they didn't come as close. Alamogordo is home to Pistachio Land with a 30-foot nut. We took a tram ride and learned that there are female pistachio trees. When I zoom up, they look like this. Male trees look quite different, and we learned why. One male tree, aided by the wind, can pollinate 20 females. No birds or bees necessary to pollinate. Who would have thought it? On our trip to Fort Stanton, we learned that it was now a state monument. It covers 240 acres and has been many things. During the Civil and Indian Wars, it had strategic importance, but it was also an internment camp for German and Japanese. At one time, it even cared for tuberculosis patients. Our drive up the slopes to ski Apache once again showed us how much land had been destroyed by the fires, but it is still a majestic view. At the top, two coyotes came running up like we had some food for them. On the drive down, we found a huge nest. I wonder what lives there. Grindstone Lake looks beautiful in the sunshine, but the drought has been hard on the area. Cinnamon-colored line at the top of the dam is how high the lake was when it used to rain. Hubbard Museum was closed, but we swore we could hear hoofbeats as we took pictures of these metal horses out front. On our last morning, we found this elk munching below our balcony. Maybe came to say goodbye, maybe just to have breakfast. As we left town, we said one last goodbye to Smokey Bear.
Hello from Independent Living. You can see they're doing curbing on both sides of the road here, in front of the building and on the left-hand side. Some work also has been done on the retaining walls, waterproofing the back of the wall. But basically, this week is the week of more yellow and more white. As we come along here, you can see two guys there working on the second and third levels. The guy on the left there is working on patching up and touching up all the yellow coating, making sure it's covering everything. And the guy on the right is putting down the white covering on the patios. He's working on the adhesive that goes underneath. That's about the most interesting thing this week. It's Wednesday, April 28th. It's about 9 a.m. It's 50 degrees and a little bit overcast and might rain later on. And now as we come around the east end, you can see they've added insult to injury by pouring concrete over my carrot patch. You think those carrots are going to work their way up through the concrete? Look down low and you'll be able to see more curbing along the south side of the building as we come around. Otherwise, there's not much to comment on this side of the building. The hatch on the roof is still open. And Black Monster's still there, straining at the constraints. Look out over C&M there to the north. Do you see the coyote? Neither do I. But there were two of them here yesterday. And now, as usual, as we come around the west end of the building, we get our long last look toward the east. And we notice that in the upper right-hand corner, they still haven't covered that patch with yellow.
There's two very critical pieces of hardware on a drone that allows it to fly autonomously. Today we're going to cover what the difference is between a flight controller and a flight computer in the context of an autonomous drone and why you might want to keep them separate for your particular project. There's two key levels of control that are going on behind the scenes in an autonomous drone. Of course, much more complex systems have many levels with specific functionality, but I want to focus on the bare minimum in order to have a drone do something useful entirely on its own. The inner loop controller is what stabilizes the vehicle either at a specified angle or vehicle body rate. Drones are inherently unstable. They require active stabilization to the motors to keep it in the air at all. Without this, even the most skilled of pilots could not keep them in the air for more than a few seconds. The outer loop controller can be thought of as a simulated pilot that is generating pilot commands. It does this in response to various sensor data used to figure out where the drone is in space to get it from point A to B without crashing. We call the board that handles inner loop control the flight controller. This is the heart of the drone that allows a pilot to talk to it with a requested vehicle state and output stabilized commands to the motors to achieve that state. A flight computer is what is used to conduct all outer loop control and requests a vehicle state from the flight controller just like a pilot does. The flight computer is the decision-making brain of a drone that makes this request as it is informed by various onboard sensor data combined with what specific task it should be carrying out. For example, GPS data tells the flight computer where it is in space. If the mission is to travel from point A to B, then the flight computer must generate the required commands to the flight controller to navigate the drone accordingly. Let's take a look at what processes are occurring in the flight controller or inner loop. First, accelerometer and gyro data is pulled from the flight controller's inertial measurement unit. This data must be processed with some sort of filter in order to estimate the drone's orientation, as individual accelerometer or gyro data cannot do this alone. The simplest and least accurate filtering technique is called a complementary filter. The most accurate filter may be a Kalman type filter. though it is very computationally costly. A magic filter is a good compromise between the other two. Next, the flight controller needs to know the desired vehicle state, or set point commanded by the pilot or flight computer. This set point is used to compute the error in the drone's current orientation from where it is desired to be. A PID controller is used to generate stabilized signals based on this error. These signals for each vehicle axis of rotation can be applied to the drone's motors according to the dynamic configuration in the control mixer. For example, to stabilize pitch, the forward motors and rear motors must receive opposite stabilized signals. We then write these signals out to the motors, which in turn generates a vehicle response. This response is again measured by the IMU, and we have created a feedback loop. Typically on a flight controller, this process runs at 1,000 or more cycles per second. So now that we can see all of the challenges that must be solved in order to complete this loop, let's see what this looks like in action. The previous flight controller loop diagram can be supplemented with additional filtering, control techniques, or safety measures. With a properly designed and tuned controller, a very fast and accurate response is possible. Next, we will look at the operation of the flight computer. This is a very broad overview of what could be happening on board, though the specifics vary based on the application. Because there is so much going on, it is not necessarily a loop either, but a continuously updated stream of input and output data. The flight computer needs an interrupt handler to process sensor data as it becomes available. A popular system used is ROS, which allows for easy access across multiple sensors, computations, and outputs. An autonomous drone might have a combination of cameras, LiDAR, or GPS on board. This sensor data is used to estimate the drone's position in space from information about its surroundings or movement, which is known as odometry. Once the drone knows where it is, a mission planner can be used to decide where to go next. A typical mission planner might look something like this. It must first decide what the current task is, for example, flying through a window. Next, the mission planner may request that the drone search for the target by either flying forward or turning around. Then once the target is identified, it must converge on it to ensure that it has actually found the target and not something else. Finally, the desired maneuver for that target can be executed. Once this is complete, the mission planner decides what to do next. The mission planner conducts its operations and in the process requests that the drone moves around. A controller is used to generate requested vehicle state set points based on where the mission planner wants the drone to be and where the odometry thinks the drone is. These requests are then sent to the flight controller at a rate of about 50 to 100 times per second. Here we can see that full and complicated process in action in a simple autonomous landing demo. The mission planner's goal here is to land on the target. It first performs a forward search and then once the target is identified by a downward-facing camera, requests that the vehicle begins to descend as the detection algorithm converges on the target. You might rightfully be asking, why not just do everything on the flight computer? My answer to that is you certainly can, and many companies such as DJI do that with their custom boards to save power and weight. But if you are assembling your own system, you may run into some problems. First, the flight computer speed is not guaranteed constant, which is a problem for stabilizing a vehicle which requires constant, high-speed operation to stay in the air. A flight computer CPU may become overloaded if excessive computations are being demanded from computer vision algorithms, which slow down the whole system or even crash it entirely. So generally speaking, it is best to have a dedicated single-task microcontroller for stabilization that guarantees the vehicle will be stabilized regardless of the health of the flight computer. In the event that the flight computer encounters an error, you can always switch back to the pilot transmitter to safely land the vehicle. So to answer our original question, the flight controller is a dedicated board to simply stabilize the vehicle, whereas the flight computer performs all the onboard decision-making and sensing, much like a pilot. Both are very important for safe and reliable autonomous drone operation. This was a very broad overview of some of the things going on inside an autonomous drone and is by no means comprehensive. I hope you've learned something and you now have a better understanding of some of the topics that need to be addressed to create a fully autonomous drone. If you're interested in some more of the nitty-gritty, check out my other video on a fully autonomous drone completing an obstacle course and how we did it.
Here at Assisted Living, we can see that they've applied the gray base coat and over that a pinkish color coat on most of the building. They're still working on some of the lower levels of the building where the drains of the EFIS system are, and down at the east end there's an area they haven't done at all. They're also working on the retaining wall, backfilling some of the areas and packing it down. Here in the lobby area we can see that not only have they poured the curbing, but they're now in the process of pouring the sidewalks along the front of the building. And skipping ahead a little to the back side, we can see that they're working on stuccoing my wall. They've put on the yellow coat and have the insulation almost all installed. And coming along the north side of the assisted living building, we can see that just like last week, it looks pretty well finished on the east end and not much progress at all on the west end. And the same is true as we round the west end. The most interesting thing to look at here, just like last week, is the retaining wall, where they're backfilling and tamping things down. They've installed special drainage mats to prevent water from building up around the back of the wall. See you next week.